in some sense. I won't even say exactly what it means. There exists a unique, in some sense, set R with all of the following properties. Well, you're familiar with many of these. If I give you two numbers, you can add them, you can multiply them, all x, y, so this notation means that x and y are elements of this set for all x, y, and r. There exists, in fact, unique. There's no confusion over what we mean by x plus y and x times y, so this unique x thing like this, as well as a thing like this. You put a dot, or maybe just without writing the dot, as we often do, which are also elements of R, such that, well, for all, so I'm going to think of how many things I'm going to need here. I think x, y, z, and R. In fact, there exist some other unique things in R as well. There's a number that's written like this, called 0. So I'm just going to write down some of these things and not comment on them too much because you've seen them before. X plus y is the same thing as y plus x. X plus 0 is the same thing as x. X plus y plus z. So there's a lot of little careful things to explain, but you know what these things mean. The parentheses means that first you form the element x plus y, and then you form that element x plus y plus z, so it indicates order of operations and all that stuff that you already know. We have similar things for multiplication. So x, y is the same as yx. X times 1 is the same as x. X times y times z is the same as x times y times z. Minus x is equal to 0 for some element called minus x in R. X times x with a minus 1 there is equal to 1 for some x, so we call this x inverse. Gotta be a little careful here, provided x is not equal to 0. Finally, here's one that mentions both addition and multiplication. Here's x times y plus z. It's xy plus xz. Okay, so I hope you weren't bored by the review of algebra. But it's interesting. Well, this theorem is a very interesting theorem, though. So there's some more stuff. There is what's called a relation. This is the less than symbol, right? We read this less than, such that. So what are some things you know about less than? two numbers that satisfy this relation. So 0 is less than x, or x is greater than 0, as you know that we say this. We know that x plus y, x times y, are also greater than 0. Exactly one of the following things is true. Either x is equal to y, x is less than y, or x is greater than y. One and only one of those statements is true. So those are things you have certainly seen before. We're almost done with finishing the statement of the theorem. I mean, the statement of the theorem is going on. I'm saying there exists an essentially unique set with all of these properties. But the trickiest part of the theorem is right now. So here is the trickiest part. The trickiest part goes like this. Suppose, this is still part of the theorem, so the set R has this property. So this is the complicated part. This is the part that we usually hide from calculus students, unless you have to take advanced calculus with me. Then unfortunately, I don't hide this from you. Suppose A is a subset of R, which is a collection of real numbers, such that, let's say, A is less. So, I mean, you know this means less than or equal to. So for all, so to say this carefully, logically, suppose that there exists, say it this way, there exists a number b such that a is less than or equal to b for all a and a. This tricky part says that there exists a smallest number b with that property. And you say, oh yeah, okay, sure. But this property is very profound, and it's so profound that it's often hidden from students the first time they think about the real numbers. So then there exists a smallest b with this property, i.e. So I'm not being very precise there. So there, i.e. there exists. If I use math symbols that you don't know, because I'm just used to it, let me know. The backwards e means there exists. This means for all. This means there exists. If you haven't seen those before. I.e. is in other words, there exists a, let's say a b prime, some special number such that a is less than or equal to b prime for all a and a, and if b is less than, or if a is less than or equal to b for all a and a, then since b prime is the smallest number with this property, b prime has to be less than or equal to b. So you need every single word in this statement to get the idea across. So here, with this, the way we say this here is that a is bounded above. So if I have a set of numbers that's bounded above, so I can find some number that's greater than or maybe greater than or equal to every element of A, then B prime is called, unsurprisingly, it's the smallest or the least upper bound. The least upper bound of A. Or it's sometimes called the supremum. Denoted by SUP for A. So similarly, in fact, it actually follows from this. So we can put it in parentheses because actually it's a consequence. Similarly, okay, in fact, let me add this. So you have to be very, very careful with this property. Also, A must be non-empty. If A doesn't contain any numbers whatsoever, this property fails. So you can add that at the beginning that A is a non-empty subset of R. Similarly, I won't write out the definition, but we should be aware that I can talk about bounded below. We have A non-empty. So if you want, take it as a problem to write out what should be the definition of this. A non-empty and bounded below. Or if you want, let's call this a problem for you. A non-empty and bounded below, so you have to think about what that means. What it should mean implies that A has what's called a greatest lower bound, or also called infima. So actually, that's where the theorem ends. All those things you already knew about adding and multiplying the rules of algebra, also about inequalities, what it means for one number to be less than another. But the trickiest part is this business about greatest lower bounds and least upper bounds. So that's an important property of the set of real numbers. Okay, so this would all be very strange if we didn't have any examples of such numbers to talk about. So let's talk about some real numbers that you already know about. So as I said, this is a tour of topology in parentheses and a lot of other mathematics along the way. The natural numbers.
John.
Yes.
Can you use this one?
The problem, I can tell you that the problem is not the marker, the problem is we need a good eraser. Yeah. But yeah, maybe this will be a little better. So the natural numbers are the numbers that you first learned about. In fact, these numbers were mentioned in the theorem. Remember there was a number called 1? We also have a number 1 plus 1, and a number 1 plus 1. So you can put, you can put parentheses around it if you want, but it's the same as 1 plus 1 plus 1. So you might as well just call it 1 plus 1 plus 1. And you have 1 plus 1 plus 1 plus 1. So as you know, we usually call this number 2, 3, 4, and so on. Those are the natural numbers. The integer integers. So this is what you get when you take the natural numbers and you include some other numbers that you know about, like the number 0. So that was also in our theorem. There was a number called 0. And then, given any number, there was a minus that number, right? So for example, you have the number -1. So 1 plus -1 is 0, things that you've seen before. -2, -3, so on. So this is a union. So this means the set of natural numbers, and you include all of these, you get what are called the integers. The rational numbers, these ones have a symbol Q. I think I'm going to have to read it. So Q is the set of rational numbers. These are all the numbers that you write as fractions, A over B. Here A and B are any two integers, although B is not 0. Oh, and by the way, this means the same thing as something that we saw in the theorem. This means the same as the number A multiplied by B inverse. Now there's a little tricky thing here, and you can add this to the definition of the set itself with the, call it a stipulation, with the extra condition or stipulation that A over B sometimes is the same thing as C over D. So that happens if A times D is equal to B times C. So that's the set of rational numbers. So, the natural numbers are a subset of the integers are a subset of the rational numbers, and the rational numbers are a subset of the real numbers, this big set of numbers with all these properties that we're talking about. So what's kind of interesting is to look at these sets of numbers and to figure out which of those properties that are in the theorem, that set of, we know that the set R has all of the properties described in the theorem. But does maybe the set Q also have all those properties? And the answer should be no, because I told you that the set that has all those properties is unique in some sense. So this well, as we'll see in a second, I mean, it's not the same as this. It doesn't have all those properties. So actually Q satisfies all the properties that R possesses, or that R does, except that one last part, that tricky part. So all the other properties, the ones with just addition to the ones with just algebra or just with inequalities, Q has all those properties, but it's that last one, that tricky one, that makes Q not as special as R. So except the tricky one. The tricky one about supremum, and infimum. So for example, I will show you, well, I will explain to you why the set of rational numbers does not have this supremum property that we described. I have the set of rational numbers whose square is less than 2. One can show, although it takes a bit of work, that this has no least upper bound. Well, this is a subset of the real numbers. So and it actually is non-empty and bounded as well. So it has a least upper bound. But the catch is that least upper bound is not an element in Q. So it has no least upper bound in Q. Here's a related fact. So if the number that you're thinking of here is the number whose square is exactly equal to 2, well, that's the point, is that that's actually not an element of Q. It's not a rational number. So there does not exist an x in Q such that x squared is equal to 2. But does there exist a real number with that property? Yes, there does, and you can show that. It follows from the supremum property, the tricky part. So, however, the supremum of x and q, or you could put r here, it wouldn't change what happens. Such that x squared is less than 2 is the number that you know and love as the square root of 2. But the point is that this is not a rational number. This is what's called an irrational number. So it's an element of R, but it's not an element of Q. So, luckily, we have a picture for R. How do we picture R? We picture R as a line. So-called real line. So, you're undoubtedly familiar with this idea of labeling points on a line as numbers. Put 0 over here, 0, 1, 2, 3, minus 1, minus 2. So for example, you have 3 over 2, which means 3 times 2 inverse. That's 1 1/2. That should be here somewhere. So here you have 3 halves, 3 over 2. And the point is that square root of 2, even though it's not a rational number, you still know where it fits on the number line. For example, 3 halves squared is 9 over 4. I think that's larger than 2, right? So square root of 2 should be less than 3 halves. Square root of 2 is over there somewhere. Okay, so actually, I think we're supposed to stop now. This is actually a good place to stop for next time. Just have said to stop at 5:30.
Okay. I thought you would say something in conclusion.
Okay, yeah, well, I said this is a good place to stop for next time, so I guess I'll see you guys Friday at 3:30. Okay?
Thank you.
to this. Again, we were saying that Friday after the seminar, it's going to be, we might meet with him to see, kind of see if he has any ideas of where to go next. Basically. Any suggestions? You're going to be busy with this.
Yeah, I'm scheduled for this, so I shouldn't change it.
Yeah, you're right. So,
yeah, I don't know.
I'll see you again.
Yeah, that's fine. You guys